Welcome back. I would like to talk today hopefully shortly, about a topic that has come up many times over the years. I want to talk about buckling and why a lot of people just don't do it right when you're doing engineering mechanical design. So, specifically, anything structural related, where you're trying to find how strong something is um, in terms of compressive strength. And I'm going to try something new here, and I'm going to show a display here, just making sure it works. So what I'm talking about is you have a typical buckling problem, and most of the time in engineering, this comes up in simplified form. You've got a column. I'll just use the typical engineering kind of nomenclature here and the drawing style. You got a column, you've got a force on it. This down here represents the fact that it's fixed, and I've got a force putting a compressive load on it. What happens is over time, you want to know when the column does something like this. And that is simplified Euler buckling. It's a very common problem. And we usually have an equation. You can use finite element analysis, or you can just do some hand analysis depending on what you want to do, where you find out the critical buckling stress is proportional to pi squared times E times I over L squared. And the proportionality here is usually a function of the constraints at both this end and that end. If you don't let this move sideways, if it's pinned, you can get different shapes. It'll buckle out in the middle here instead of just sideways like that. Then you have right here, you have your elastic modulus, which of course is a function of the material, and your cross-section moment of inertia, which is a function of the column's geometry. However, what happens when you have something that looks more like this? You have a column, it's in compression, or it could even be a beam, but it's got a little extension here. And oops, let me change the colors here. So it's what I want. I want the red color, not the blue. So you also have a compressive force on it, but now you have this little moment arm on the end. So what's going to happen there is it's going to cause this to bend out and have a different shape. And this gets really complicated because this is a nonlinear geometry problem. As soon as you load up this geometry right here, it starts moving in an appreciable way. Now, maybe if it's very small loads, you might not notice this, but when you're trying to design, when you're trying to save weight, which means things are not going to be any stronger than they have to be, these deflections start to really matter and really start to affect your design. And depending on how you do this, if you just use this simple buckling equation, oops, did not mean to move that there. You just use a simple buckling equation, or if you use a linear finite element analysis, this isn't going to help you. You're not going to be able to use an equation like this. So this equation is not going to be any good. And a lot of common problems, even if they're somewhat more restrained. Let's say we have a sliding. That's not the best drawing there, but we'll make do with it. Let's say you have a sliding attachment so that this cannot drift sideways. You also have a compressive load. This could be more like a beam in an airplane wing or somewhere else. But you're restraining that movement there. like I said, you have these different configurations where now you can have some bending out in the middle. It's not going to bend here because it's restrained. The truth of the matter, though, is that most of the time when you make a beam or a column in real life, there's going to be this natural distortion when it comes out of factory. Nothing's ever perfect. So you have to take into account this delta of this being not a perfectly straight column. Not only that, but this load is hardly ever perfectly straight right in the center of the cross section at the centroid. Not only do you have this compressive load, but you also have often this moment in reality due to either a situation like this, which just pure geometry creates a moment. Maybe the load isn't perfectly centered, or maybe you just have something designed at a corner where it's going to take a bending load. So that is the first form of nonlinearity for buckling that a lot of people miss whenever they do this analysis. So one, we'll say forms of nonlinearity. One is nonlinear geometry. So this is incredibly important, and it's very common that people don't take this into account. And what happens often in industry is people will say, well, we're not going to take into account nonlinear geometry, so we're just going to throw a high factor of safety on it, maybe 5. And maybe that'll cover you. Maybe it won't, but that means that you are not actually calculating the physics of the situation. Excuse me. And there's another main problem here. By the way, this nonlinear geometry can not only affect the shape of this beam here, or the column, it can also affect the moment of inertia. If you have a really hollow cross section where, let's say it's just a hollow rectangle, it's not solid, and you load it up, maybe it distorts a little bit like this, maybe get some waviness in it, maybe if you have a circular cross section like this, maybe it goes oval, elliptical on you like that. This, especially if this ovality here is a shrinking in this direction, and this is your bending axis right here, this is going to cause this moment of inertia to drop. And if you don't take this into account, you can vastly underestimate the capacity of your column. So the other thing that people miss is number 2, nonlinear material. What do I mean by that? So in this equation, this simplified Euler equation, we have E, which represents the elastic modulus. But there's something, I don't know if you're familiar with it, there's something called the tangent modulus. Sorry, I had a little brain fart there. So tangent modulus, what in the world is that? So if I've got a couple of axes here representing the material behavior, I have got the stress, the compressive stress that you're seeing in a material, and I've got the tangent modulus. So there's a kind of fictitious vertical line here where your normal elastic modulus is. If you go online and you go to MATWeb, or you look at the MMPDS, or if you look at whatever reference handbook you've got, they usually show this modulus E as the critical value that they give you. They don't give you much more than that. Sometimes you get lucky and they actually have some curves for tangent modulus. But not always. So you use this value of E and you assume it doesn't change. Well, here's a problem. You've got a line here, another dotted line on this other axis. And this is this horizontal line is right at the yield strength of material. So when you are functioning at a very low stress in material, when a material is very lightly loaded, it is essentially behaving as if it's not softening. It's right at the value of E here. But as you load it up, as the stress increases and gets closer to the yield strength of the material, you move in this direction on this line. The higher that your compressive stress goes on your column, the lower your modulus goes. So when you get to the yield strength of the material, your modulus goes from 1.0 times E to more like, sorry, did I mean to move that around again? It goes from 1.0 times E to sometimes more like 0.1 times E. And that's because you have this something like a softening effect. That's essentially what happens when you have a material under compressive stress. So to really do this right, you need to use, if you're doing this by hand, which you can do, and I'm planning on showing exactly how you do that later, but you can have this equation where it's proportional to, of course, your pi squared, but you have to use your tangent modulus, and you have to use your I if it changed over L squared. So instead of using your normal modulus, use your tangent modulus. The tricky thing is, as you calculate, this P crit changes and affects your compressive stress. And that changes your tangent modulus. So you get this into the cyclical thing where you are going from, so what happens is you go from what is normally a very simple, straightforward problem where you just calculate a critical buckling load, or you look at eigenvalue buckling results in a computer, and you have a number. It just runs it once, boom, you're done. Well, that's not how you can actually solve the buckling problem. You need to iterate and take into account the changes in geometry and the changes in material as it gets loaded up. Then you calculate where, through this iterative process, where you expect it to actually fail when you consider both a nonlinear material and a nonlinear geometry. Only then do you know a failure point and then design to a factor below that. That's the only way you can actually have a factor of safety. If you go through this and you go and use these equations, especially the naive form, this simple Euler buckling right here, and you don't take into account nonlinear geometry, you don't take into account tangent modulus or any kind of nonlinear material effect. If you just do that naively and you say, well, let's not worry about it, we'll use a factor of safety of 3 or 4, you could actually have a design with a negative factor of safety. And I've seen this. I've actually seen where something is so nonlinear due to both geometry and material where you can run the calculations linearly and you can be off by a factor of 5 or more. So this happens, and it can catch you by surprise. Hopefully it's caught on a test, or you are working in an industry that's more regulated, like the civil engineering, where they actually have to take into account these things. But a lot of mechanical engineers do not know this. So that's it for today. I just want to go over the brief things that most people do not understand about buckling. And I'll see you soon.